Let me just do it again, just for recording. Okay. So as you see, this is the course on optimal transport. Professor Sumikpal and I'm teaching this course, and then please check the website, and here are references. And I really recommend this book, Topics on Optimal Transport, but there are other excellent references. And if you are interested in machine learning AI, then you want to check this computational optimal transport. And if you really want to understand so-called gradient flows in a very rigorous manner, you want to check this book, Gradient Flows. And there are many other papers that you may want to read. And so Zoom lectures like this one, and then we record these lectures. And please register for Slack, because that could be the main platform for our communications, okay? Okay, we assume that you know some measure theory. Okay, any questions? All right. Okay, so the first 2 weeks I'm going to teach. So this week consists of really the basics of optimal transport. And then afterwards, Professor Pai teach 2 weeks, some kind of geometric aspect of optimal transport. And after that, I will come back to teach more. And then these are like topic schedules for this course. And after that, we have many other topics like this. And if time allows, we will do some additional topics which are kind of related to some recent developments. Okay. All right. Yeah, let me start the discussion of optimal transport. So optimal transport, I mean, who knows? Maybe somebody like 600 years ago already thought about this problem. But in literature, the first person who considered optimal transport theory is Gaspard Monge, and that's why we call optimal transport sometimes Monge-Kantorovich theory. Here, Kantorovich is another like big name in optimal transport. So Monge considered some problem, but later. But it was kind of forgotten. He wrote some kind of memoir, some kind of letter or notes on this kind of optimal transport phenomena, and it was kind of forgotten, probably like 100 years. Then later, Kantorovich, probably from very independent reason, considered the same problem, and Kantorovich kind of reformulated. I mean, he provided a different formulation of Monge. And then, because of his formulation, he was able to develop this so-called duality theory, which we will learn, and which is actually the starting point of so-called linear programming. So Kantorovich is like a founding father of linear programming theory. I mean, one of the founding fathers in linear programming theory. Okay, we consider linear programming too. And there are many other people. I just list some people I like. These are people mostly in the PD side of the theory, okay, starting from Brenier and Caffarelli, Mecan, Otto Villani, Ambrosio Turingo, and many others. And if I count generously, we have now 2 Fields medalists in this area. Okay. So what is optimal transport? It is about optimization. What do you optimize? You optimize some measures. Okay, that's why your measure theory is your prerequisite. Okay, is my pronunciation good? Do I have to be slow? Okay, fine.
I understand.
Okay, thank you. Okay, so why do you want to learn optimal transport theory? From my point of view, it's because it is connected to many other things. It's very like fundamental in that way. So it has connections to problems in analysis, geometry, probability, like rich curvature, rich flow, singular spaces, inequalities, isoperimetric logs overlap, stochastic processes, and convex geometry, and so on and so forth. And PD, Monge application, geometric optics, nonlinear diffusion. So nonlinear diffusion is where you have gradient flows. Okay. It doesn't have to be nonlinear, but just in particular, one of the major breakthroughs in optimal transport theory is that you can understand all these porous medium and many other equations in a unified way as the gradient flow of certain functional in some geometric space. And fluid mechanics, surprisingly, it also has a connection to fluid mechanics. And actually, one of the most recent development, one of the, not most recent. So after Monge and Kantorovich, the problem has been considered in, let's say, optimization theory, like linear programming, or in economics, because economics wants to optimize things, and statistics, and also some kind of probability theory. But why optimal transport is now very popular in PDE theory with this like two Fields medalists and many others. The starting point is Brenier, Jan Brenier. He considered, he wanted to understand Euler equation, the fluid mechanics. And he kind of tried to develop some numerical analysis for understanding this fluid dynamics. Then somehow in doing so, he wanted to have some kind of projection of your object going outside of the regime you want. And you want to, because in the numerical simulation, if you do computations, then objects may not stay in the regime you want to stay. Okay, it goes outside, and you want it back to your regime. Okay, then you need to consider some kind of projection to it, and that projection is an optimal transportation problem. That's how Brenier connected optimal transport to fluid mechanics and more generally to PD theory. Okay, that's the kind of starting point. So Brenier, in doing so, basically connected optimal transport theory to Monge amplification. It's very strange. I mean, Monge was the founder of optimal transport theory, but Monge amplification is connected to optimal transport theory rather like 100 years later by Jan Brenier. Okay. All right, and then there are also some interesting development in free boundary theory, and I'm also involved in such a thing called Stefan problem and ice melting, water freezing, and so on. Okay, so Villani made this very wonderful comment. In my opinion, this abundance only reflects the fact that optimal transport is a simple, meaningful, natural, and therefore universal object. And you will learn that optimal transport is really simple thing. Okay? It's very simple. Sometimes it's confusing, but it's simple thing. Okay. So once you understand that simple thing, you can see many things from a different point of view. I mean, from the optimal transport point of view, then things will look different than what you usually see. Okay. Okay, and there are also practical applications like in image processing. And using optimal transport theory, you can generate this kind of images. And you will learn this later. So you have donut shape, let's say hippopotamus and dog. But then the question can be, how can you interpolate these pictures? And you can generate these like different pictures resembling like donut, hippopotamus, and dog in a different way. Okay. So optimal transport can handle this kind of problems. Also, machine learning AI, I mean, because data sets are measures, okay? So anything optimizing data sets can be related to optimal transport because data sets are measures and optimal transport considers optimization over measures, okay? By the similar reason, it is related to many statistics problems. And a very interesting directional research is this stem cell research. I mean, how our cells develop. Okay, so cells, I mean, organisms develop over the time, right? Birth and then grow and death, and then we want to understand the mechanism how that kind of things happen. And optimal transport theory, at least theoretically, and sometimes in real practical examples, can help understanding, can help us understand such phenomena. Okay, so In particular, Professor Jeff Schubinger in our department was one of the pioneers in that direction. Okay. Also, there is other important people in our department. Okay, Jeff Schubinger also, there is Khan Lauder. So Khan also is a professor in our department, and he also considers optimal transport in the context of biological problems, how to understand, for example, protein shapes. And there are, I mean, economics is basically the classical area where optimal transport can be applied. So, in fact, as I wrote here, Kantorovich won Nobel Prize in economics because of this development of optimal transport theory. Okay. In finance, yeah, so there are some recent very interesting development in finance related to particular stochastic processes and optimizing things over stochastic processes. And optimal transport theory can be considered there, giving some nice things. Okay. Nice. So far, so good. Any questions? Okay. Question? Question? All right. Okay, now that's for background, and let's start the basic, the real basics. So optimal transport is an optimization problem. Okay, and optimization problem in general can be written in this very simple way. You want to minimize or maximize. Okay, so in this is like minimization of certain function depending on some variable. Okay, and okay, the variable can be, let's say, a variable in Rn, or it can be some variable in, I don't know, some Lie group or whatever. I mean, it can be some variable, okay? But when you consider optimization problems, you have to restrict your variable to satisfy certain conditions. So that is called constraint, okay? So let me repeat. In optimization theory, you have the objective function. You want to, let's say, maximize the profit of some company. You want to, or let's say, minimize air pollution of like Vancouver, right? That's the objective function. And then for the objective function, but objective function of what? The function should depend on some variable, right? So that variable is called the decision variable. Like to optimize the profit of your company, I mean, there are many decision variables to consider. Right? Let's say the number of employees and the salaries and like where you want to spend, how much you want to spend on marketing or customer care or storage and whatever, right? So that how much in what? That is something you need to decide, okay? And the result, the profit of the company will depend on your decision, right? So that's why the objective function is a function of a decision variable. So in optimization problems, you should have this, at least this objective function and decision variable. And for the decision variable, let's say the salary, for example, in a company, you don't, I mean, okay, the better salary, the higher salary, the better in general, right? But the company cannot just provide you infinite salary, right? So you have constraint, obvious constraint. So this is like probably the most optimization. Any interesting optimization problem will have constraint, okay? And then the constraint can be written in this simple way, like your variable should belong to a certain set, and the set where all the conditions for your constraint are satisfied is called feasible set. Okay, just name. And then, so you say an optimization problem feasible if you can find if your feasible set is non-empty. I mean, sometimes in some optimization problem, your feasible set can be empty, right? Let me show you. You maximize or minimize. For example, minimize, let's say x subject to x. Okay, minimize x. X is less than or equal to 0. Okay, right? So this is a nice optimization problem. It has everything. It has objective function, decision variable, and constraint, right? And this problem, oh, sorry, this problem is feasible. Okay, but if you say x is also bigger than 1, okay, then this problem is not feasible. Okay, okay, then why are you considering this kind of feasibility? I mean, feasibility should be okay, but sometimes you may not know feasibility of your problem. Okay, there can be many, like you can imagine having some function like x1 plus 2x2, whatever, I mean, and then subject to some conditions like x1 plus 2x is less than 1, x2 plus x100 is bigger than 2, and so on. Suppose you have like 100 such inequalities, then how can you check whether there is a solution satisfying all these inequalities? So sometimes feasibility is non-trivial. Okay. Okay. It is like this. You are the owner of a company. You want to achieve something. You want to maximize the profit, but you want to satisfy certain constraint on each of these, like let's say spending on marketing, salary, and so on. But your conditions you want to suggest may not be feasible. Okay. So checking feasibility of the optimization problem is very meaningful and sometimes very non-trivial. Okay. Anyways, so these are main ingredients of optimization problem in general. And in optimal transport, then we consider measures, transport plans, and cost functions. Okay. These so transport plans, these are decision variables, and cost functions are related to objective functions, and measures are related to constraint. Okay, so we will learn these step by step. Okay. So far, so good. Questions? Okay. No question? Don't be shy. It'll be too easy so far. Okay. Okay, so let's consider measures. So measures are, I mean, very common. Measures capture randomness of some phenomena like this, like Gaussian distribution and distributions. I mean, you can see, for example, images as distributions, like each pixel has some kind of density, right? So you can view this as a mass distribution or over this two-dimensional box, okay? So this image corresponds to a distributional mass. Also, like temperature can be considered as a distribution. Each point has some value. And data sets are distributions. Like here, you may have a frequency of the data at each point. And this is a distribution over two-dimensional space in this picture, but you can imagine that data sets are like distributions over 100 or 1,000 dimensional spaces, right? So what are interesting, I mean, sometimes low-dimensional phenomena are interesting, but obviously in statistics and AI, very high-dimensional phenomena are of interest. Okay, so measures are relevant. Okay, so how they are related to optimal transport. And sometimes I will call optimal transport problems as Monge controversy problem because these are two important founders of the theory. Okay. So Monge controversy problem, optimal transport problem, is about matching two or more measures. Okay. Example, you have, let's say, Boyers. Distribution of Boyers are that you have, let's say, the Boyers income and let's say like a location, whatever. Then each Boyer can be placed in this kind of space. Okay, right? Then you have also sellers over some locations. This location, and you want to match this some buyers to some sellers. Okay, right? Maybe easier example is, okay, it's not me. Easier example is you have students over location, like in Vancouver, you have many students located in different areas, and then you have schools located in Vancouver. Then you have, okay, so this is Vancouver. We have students, many students, and then you have, oops, Vancouver, and then you have students. Okay. If I keep doing this, I just spend most of the lecture time. So let me stop now. Okay, then you have schools, some schools, right? So schools has distribution and students have distribution. Then you want to match which students goes to which school. Oh, sorry. Right? And then, yeah, okay. And then like you have some photo, and then in a photo you have pixels, and then you have pic as distribution, and then you have another photo, it has pixels as distribution, and you want to sometimes match these two pictures. Like for example, let's say you saw me when I was a baby, okay, and then you saw you now. I mean, my photo maybe like several decades ago, and then my current picture, and you want to, let's say, guess how did I look when I was like in 20s, like in your age. Okay, I was much more handsome than now. And then to do that, you need some kind of matching between the past, the very past, and then current. And if you know the matching, you can kind of use that matching to interpolate this very past and the current to see something in between. Okay. That's why it's something relevant. And also, bacterial population today and bacterial population tomorrow. Which bacteria are developing to, okay, or which bacteria went to that new location, whatever. I mean, you want to understand how, let's say, cells, the bacteria move, okay, maybe in a certain region, and then let's say this bacteria move to some other region, and you want to understand which one went to which. Just by knowing only this distribution now and this distribution tomorrow. Okay, matchings. I already explained why matchings are relevant. Okay, then such matchings can be described mathematically as transportation plans. Okay. So what are transportation plans? Okay, so these distributions are nothing but mathematically just measures, okay, positive measures over some space. Okay. So let's say this is your x space, and okay, I should use. So this is your x space, this axis, and this axis is your y. Y0 is there. Oh, right. This is your y space. Did I miss? Okay, right? Oh, fine. Okay, right. So then you have some distribution over your x space like this, mu x, and over your y space, you have some distribution like this. Okay, like bacteria today and bacteria tomorrow, bacteria populations, and then which bacteria? I mean, the bacteria here you have like this many bacteria at some location, and then you want to see where these bacteria went in the new locations. Okay, then in this XY space, you have, let's say, in this case, XY. Each point is like XY. So you have X point and you have Y point. Okay, so a bacterium is in here means yesterday it was in this location X, and today it is in location Y, right? And then you can just distribute the bacteria population according to these coordinates. Where was it yesterday, and then where is it now? Okay. Then at each such coordinate locations, you can put those bacteria. Then each such assignment, where was it yesterday and where is it now, can give us some kind of distribution over this product space X times Y. Am I making sense? Or simply, yes.
Oh, yeah. So were you saying that mu would be, mu would be the measure on the bacteria or of the distribution of the bacteria from yesterday, and then
Yes.
yeah, okay, yeah, it would be, and then nu would be the one for tomorrow or for today, I guess.
Yeah, yeah.
Okay.
Yeah,
Thank you.
sorry, I messed yeah. So yesterday and today. Okay. So you can view it this way. Suppose you have some measure on this product space, some measure. Then that at X and Y, this let's say mass or some particle or whatever this point correspond to X location in X space and Y location in Y space. So such measure can be understood as like matching the points X distributed according to mu with points Y distributed according to nu. Okay. So in probability or statistics, this is very like common object called coupling. So another name of this is coupling. Coupling between two distributions. Okay. So measure on X times Y can be a coupling or transport plan between the measure mu on X and the measure nu on Y. I mean, not every such measure on the product space can be a coupling on X and Y, mu X and mu Y, right? So the only condition that transport plan to satisfy to be the transport plan between mu and nu is this. namely this measure on the product space, so measure on X and Y has marginalized mu in X and nu in Y. Okay, what do you mean by this marginalized? It's like this. You have this distribution, right? So at each location you have this mass, okay, and bring that mass and project it just to this X space, okay. For this, you have mass, project it down to X space. Then you will have the corresponding distribution, right? So that projected distribution being the same as the given distribution mu is this condition, okay? Am I making sense here?
Yeah, I think so.
Okay. Likewise, you can just project down this mass over this X times Y to the Y space. You just bring it down there. So just imagine you have just particles there, right? You just bring this particle down to this Y coordinate location. Then you collect these particles, then these particles will have some density or distribution, and that distribution is this projection, okay? And then that being the same as the given distribution nu, that's the other condition. So if a measure on the product space satisfies this marginal condition, then projection to X is the same as mu, and projection to Y is the same as nu. Then we can call such a measure, in this case pi, a transport plan between mu and nu. Okay. Well, sometimes if you like probability or statistics, you may call it coupling. But in this course, because it's optimal transport course, I encourage you to use transport plan, okay? To not confuse me, all right? Okay, questions? Yes.
So how does this projection work mathematically? Do you integrate again?
Oh.
You integrate away the other quantity?
So even, okay, so I should, okay, so maybe, okay, I'll come back to that, okay? Actually, this in the next slide, right? So, so mathematically, I can, okay. Okay, in my opinion, what I said about these moving particles down to X and to Y, that is very mathematical by itself, but okay. But maybe if you want some other way to express it, here's a way, okay? So probability measure, let's just assume that these mu and nu are probability measures, okay? The total mass is 1. Oh, by the way, before saying that, so suppose you want to find a transport plan between mu and nu, okay? And there is at least one very important condition, both mu and nu to satisfy, to have a transport plan. Right. So you see, the pi is some measure on X and Y, X times Y. And if you project this, this mass down to here, the total mass does not change, right? Because imagine you just have particles and just brought down the particles to X space. So number of particles didn't change. So by that reason, the total mass does not change. The same here. If you project it down to Y, the total mass does not change. Okay. Consequence, this mu and nu should have the same total mass. Otherwise, you cannot find the transport plan given in this way, this sense. Okay. Am I making sense?
Youngman, there is one question
Yes.
From Emma, who's asking, does the total mass have to be finite or can they also be both infinity?
Wow, that's an excellent question. They can be both infinity, but then of course you don't have this. Yeah, It is like one cannot be finite. So it cannot be that one is finite, the other one is infinity. If one is infinity, the other one has to be infinity. Then you can consider the infinite mass distributions, and you can consider some kind of matching between them, transport plan between them. And I don't usually consider them, but then you may consider some kind of optimal transport between them. It is possible, but it's not the way we want to present, and because they're often I mean, we will consider so-called cost of transportation. But if you have infinite mass, then sometimes you may have just infinite transport cost. So there's nothing to minimize and so on. That kind of things may happen. So I don't want to that infinite mass case deeply at all, but it's a really excellent question. So you can, of course, consider infinite mass to the optimal transport, but that is not really the main kind of interest of this course. Did I answer the question well? Sumi, is my question okay?
Yeah, that's good. Thank you.
Yep.
But that's really excellent question. So please ask this kind of question, right? So you want to think out of the box. Okay? Just don't stay in what I say to you. Okay. All right. So then, so to have transport plan, the mass of these mu and nu should be the same. So I just normalize them to be 1. Okay. Okay, just because Emma asked this excellent question, and one comment is that you can also consider actually the mass transport between distributions having different total mass, but then that transport does not follow this definition. Okay, right? You should create something similar but not the same. But we will learn the so-called unbalanced. We will consider the so-called unbalanced optimal transport, but in the last week. So you have to wait for a long time. Okay. Okay. Then a transport plan. Oh, maybe I'm too slow. Okay. Okay. The projection of measure and satisfying the marginal condition can be written in this way. Okay. It's like this projection of this mass to this x direction, and to get this distribution is the same as you consider this, let's say, vertical line, consider all y coordinate, and then you integrate this mass along. I mean, you just take the slice, okay, and you integrate that slice of this mass along this direction. That is, if you really think about it, that is exactly the same as putting that particles down to that x location. Okay, that is these conditions. Okay. Okay, so a transport plane between mu and nu is the measure, positive measure and negative measure, satisfying these marginal conditions. Okay, integrating in y will give you mu, integrating in x coordinate will give you nu. So maybe to be more precise, this is integrating in mu is a 2-variable measure, x and y, and then you integrate in y, then you get mu x, and then you integrate this mu xy in x, then you get mu y. Okay. Right. But that kind of marginal condition, I'm bring these particles to the X space by this projection. It's an example of something much more general. Then much more general is called push forward. Okay, it's just the basics of measure theory. You suppose you have some two spaces and you have some function. Measurable function. Measurable function is something nice, okay? Some nice function, so reasonable function between two spaces, okay? Then there's this notion of push forward of one measure to the other. So this map or function from X pushes this measure mu on X forward to this measure nu on Y. We say that if the following holds, okay? What is it? You have X space and you have Y space. In Y space, you have a measure, let's say some measure. And on X space, you have measure mu. Okay. And then pick any, let's say set, in this case, let's say B here. Okay, in the Y space. Okay, here is the function f from X space to Y space. And you take inverse image of this f inverse B. Okay, then you can measure the size of this f inverse B with respect to mu. That is what this is. And then you can measure the size of this B in terms of nu. That is this. And this condition, f push forward mu to nu, is the same as the equality between these two sides for any measurable set B, basically for any set B. Okay? Right? So there's particle interpretation of this. You have particles here. I just bring this particle following this map, so following that function f to this location y. I just bring this particle to just follow x and then bring them to location y. Then that operation is exactly the same as this. If you really think about it, okay? So if you don't like this mathematical thing, just always remember this particle interpretation. Your particles, you just bring this particle to this y space following the function f. That is exactly this operation. And then, this operation, the push forward operation. And then you have distribution of those new particles there. And that distribution is the same as nu. That is this condition. Okay? And so the previous marginal condition for the transport plan is the same as this projection to X pushing, and this projection to Y pushes forward pi to nu. So these are equivalent conditions. Okay. Question about the push forward operation. By the way, can you see the slide? Sorry. Can you see the slide in full over the Zoom? Do you see what I'm writing here?
Yeah, we can see it.
Can you see? Do you see it?
Yep.
Oh, okay. Okay, any question? Okay, so push forward is really, really important concept. You want to be fully familiar with. But whenever you get confusion, just remember what I said. It's just nothing but moving particles, just following the given function. That's what push forward is. Okay? But when you really do some mathematical checking or some computations, you want to use some expressions like this. Okay. But intuition is just what I said. Okay. Okay, now, so given two marginals, a transportation plan between them is a measure pi satisfying these two marginal conditions. Okay, suppose you have two marginals mu and u. They have the same total mass. Okay, can you find a transport plan between them? Maybe it's better to consider two examples. I mean, some examples, not just two. Okay, just two. Suppose you have Dirac delta mu at x and Dirac delta at y as your mu and u. What should be the transport plan? Yeah, just x to y. So in this xy space, you have x location and y location, and your transport plan should be a measure there at xy. Okay, so your pi has to be Dirac delta at xy. Okay, easy. Now what about the next one? You have mu Dirac delta at x, and y is something like you have some kind of ball, and then you have the measure over that ball. I mean, here the point is that they have the same total mass because you normalize this measure, okay, like this way. This is a uniform measure on the ball. Okay, so this is a characteristic function, so it looks like if you have ball bx, then the function, the measure looks like, so this is characteristic function. The height is 1, that is a characteristic function brx, and then this one has this total mass, the same size of the mu of b, sorry, the volume of brx. You just divide it by the volume, then you have a probability measure having total mass 1. So they have the same total mass. Okay, what should be the transport plan between them?
Just multiply them.
Multiply?
Right. BRX. This X is different from the delta X.
You're right. So this should be, no, this x is the same as this x, right? Okay. But this is function of y. Don't be shy. I mean, just, you don't have much time left, so you want to be quick.
Yeah, always take the product measure.
Right. So let me just do this example in a more detail because this is really important and it's trivial but very important example. So here you have a ball of radius r like this, and you have a Dirac delta at x. Okay, what should be the transport plan between them, right? It's very easy. You just move, I mean, so imagine Dirac delta as like a group of particles located at the same location x, okay? And then this nu, it's just group of particles located evenly over this area or this region BRX, right? Then what should be the transport plan? You just move each particle here to each location, kind of evenly. That is a transport plan. Okay. Okay. How can we describe it more mathematically, if you like? Okay. What I said is already mathematical, but just for your taste, maybe let me just try to the next. So at X, you have Dirac delta here, and then you distribute it over evenly over this location. So somehow in this product picture, this is the same X. In this product picture, you just put this the mass here kind of evenly, but it's kind of Dirac delta. So one way to write it is this: you have this measure nu, which is just a uniform measure over here. Okay, but then at here, if you project it down, you should get just Dirac delta. So in this case, just this one works. The tensor product between two measures. Okay? So what tensor product does is exactly what I said. You just bring this mass and then distribute it over these target locations, following the measure nu. That is what this tensor product does. Okay, so you can just this nu doesn't have to be a uniform measure like this. It can be some other measure. Okay, but just the tensor product will do exactly do the job. And then if you have two like probability measures in general, you can imagine that such a process, such a procedure, such an operation will give us a transport plan. Okay. Am I making sense? So maybe I should give a little bit more detail here. So you have, let's say, mu distributed over X, and then nu distributed over Y. Then this mu tensor Y, tensor nu does this thing. So you have at each location X, you have this much of mu X, right? Okay. It's kind of mass at that location. And then you just distribute that mass, okay? Following, I mean, over these use the different color. Over these locations, okay? Following, following this distribution. Okay. Okay. So just at each vertical piece here, you just follow the same pattern as nu. Okay. It's basically here. This measure is something like Dirac delta tensor product nu, but it's not exactly Dirac delta because at X you don't have Dirac delta but mu X. So it should be called a mu X tensor product nu, something like this. Okay, you just have this total mass at X this much, and then you just distribute that total mass following this pattern of nu. Okay, and you do it at each location. That is what this tensor product is. All right, making sense? Okay, so there always exists an optimal a transport plan between those probability measures mu and nu. Okay, whenever the total mass are the same, you have a transport plan between them. Okay. Okay, then among those transport plans, we want to consider optimal ones. Okay. And you can imagine that, I mean, this is very special case of transport plan, but you can imagine there can be many other transport plans, right? Like consider the transport plan between students and schools. There can be many ways to assign students to different schools, right? And for such transport plans, how can we consider optimality? Okay? To consider optimality, we need to formulate this objective function. So far, transport plans are just decision variables. In which way we want to assign x to y. That is transport plan. That is what you want to decide. Okay, decision variable. So transport plans are decision variables in optimal transport problems. Now we want to consider the corresponding objective function. What do you want to optimize? Okay, we want to optimize according to some cost. Let's say in this students to school assignment problem, I mean, you don't want to assign the students living in, let's say, UBC area to a school in, I mean, elementary school in like Surrey. Okay? You don't want to do that. Or Richmond is too far for elementary school students. So you want to put students to the nearby schools. Then in that case, what you want to optimize is probably the distance between the students and school. But you have so many students and many schools, so it's not just optimizing the distance between one student and one school, but group of students and group of schools. So somehow you want to optimize the average, the average of the distance between students and schools. Okay, and that's the idea. The average, but because assigning students to schools is like a transport plan, and such a transport plan will cost some average distance between the students and school, right? And you want to optimize such average distance. Okay. So now back to this students and school. Just for each student and each school, assigning one student to a particular school will give us some distance, right? That is like the notion of cost function. So given xy, you can consider some cost moving a unit mass at the location x to the location y. Like in the previous school students example, it's just a distance. But cost function can be anything, okay, depending on your particular application. But in optimal transport theory, the most important cost functions are the distance or distance square. But you can consider many other types of distances, cost functions. But these are probably two most important cost functions. Okay, any question about cost functions?
You usually choose our cost function, the output of the cost function to be non-negative numbers only.
Usually, yeah, non-negative makes sense because like a cost is like a positive quantity. Yeah, but it doesn't matter. You can even assign like plus infinity depending on, like for example, assign you don't want to assign students in UBC area to a school in let's say I don't know Richmond or Seattle, right? Then one way to avoid it is just to put infinite cost for such an assignment. Okay, but also yeah, it's also okay to have some negative cost function. Okay, just it depends on your actual application, which cost function you want to consider. But theoretically, the theory of optimal transport has been developed heavily on these two cost functions. So this is the cost function Monge originally considered. actually also Monge and Kantorovich. Okay. And this is a cost function Brenier considered. So this is a cost function that has this deep connection or very strong connection to PD theory. I mean, both have such a connection, but this one has more as an obvious theory. So this cost function is very popular in optimal transport theory. It's like in analysis, L2 theory is more popular, I would say, than L1 theory because of this theory of Hilbert space and all others, right? So kind of similar. The square helps a lot. Okay. Yeah, okay, these are examples. And then what is the total transportation cost? So you have your transport plan, your decision variable, and you have your cost function for each xy. So the transport plan is a measure on the space, on the product space xy. So you have some measure here. Okay, pi. Okay, then at each point xy, locating, let's say, point x to y, your cost function cxy. Then this pi, the transport plan, will assign how much of mass should be transported from x to y, right? Then for that, how much of mass, you just multiply this cost function. How much does it cost for unit mass to be matched between x and y? Okay, so that cxy is for unit mass, and then pi xy gives some mass. So the cost for that pi xy is cxy times pi xy. That is this. And then you have so many points here. So you just integrate this over xy. So this is the total transport cost. So this is our objective function. Okay. So you want to minimize this objective function for these decision variables pi, satisfying these constraints. The marginals are given mu and u. Okay. So then you have the decision. You have mu and u, and you have decision variables, the transfer plans between mu and u, and the constraints are pi has this x marginal mu and y marginal nu, and pi has to be a measure, non-negative measure. Okay, that's the constraint. And then objective function is just this transportation cost for pi, and you want to minimize. Okay. So such a problem is a particular example of the so-called linear programming problem. Okay. So if you consider just finite space, that your mu is just a measure on the finite set of points, and nu is a measure on the finite set of points, and the transportation cost is just between some finite set of points and finite set of points, cx, ij. Then instead of writing these integrals, you can write the summations, and then you can see that this problem can be written in this way in over finite spaces. Okay. Then if you look at these expressions, the variables are so pi 1, 1, pi 1, 2, and so on, pi 2, 1, pi 2, 2. So these are the decision variables. Okay. So you have, in this case, there's m times n decision variables. Okay, m and n, or m and n decision variables, and then all these expressions are linear expressions. they are either linear equation or linear inequalities. Okay. Right, linear inequalities and linear equations. So everything is like linear. So an optimization problem with only linear expressions is called linear programming. Okay. And optimal transfer problem, when here pi is a decision variable and integral is linear with respect to pi. So every expression here is a linear inequality or linear equations or linear function. So optimal transport is a linear programming problem. Okay. However, for this decision variable, the dimension for that decision variable is what should be the dimension in typical cases for that decision variable pi. Pi is a measure on the product space. Let's say x is r and y is r. Then what should the dimension for the pi's transfer plans? What? No, dimension. So pi is some variable. So variable belongs to some space, right? What should be the dimension for the space for the decision variable pi, where mu is a measure on R and nu is a measure on R. Let's say it's like a continuous measure mu. I mean, I don't know, just fx dx. Nu is let's say gy dy, something like this. And fn and g are like continuous functions. Then what should be the dimension for the transport plan between them? So here, just if you just consider these conditions, basically the transport plans are measures, okay? And if you have just R and R, then what's the dimension of the space of measures on R2? Infinite. Okay, you have a lot of such, I mean, infinite dimensional spaces of such measures. So this problem, optimal transfer problem, are typically infinite dimensional problem. Okay, but sometimes you can do this finite dimensional problem. Okay, you can approximate your infinite dimensional problem with this finite dimensional problem. Sometimes you just want to consider some finite dimensional problem. Okay. All right. But anyways, the point is that Monge-Kantorovich problem or optimal transfer problem is a linear programming problem. So the theory of linear programming can be applied to optimal transport. And in fact, Kantorovich considered a linear programming problem just to, I mean, this problem was his starting point to develop things in linear programming. Okay. I have many other things. Okay, so maybe let me just spend 1 more minute. So here below, I just wrote some very simple example. You just want to consider this by yourself. Okay, read it. Okay, and then okay, let me just skip this. Okay, then the question is whether an optimal transport problem has a solution. Okay. Okay, optimal transport is feasible, right? You know that given mu and nu, there's always transport plan. So it's a feasible problem. So now we can consider whether there's an optimal solution or not. Okay, and so existence of an optimal transport plan. Probably I will discuss this on Friday. Okay, we can stop now.